This video is going to be a geometric explanation of special relativity. Special relativity is Einstein's theory which relates space and time. When it was first published, it revolutionized physics and it captivated people with its strange predictions. This is how I was able to wrap my head around the subject because the standard introduction of a handful of disparate formulas really wasn't working for me, and I had always heard that Einstein's theories were about the geometry of spacetime. So I sought to find a more intuitive and self-contained explanation of the theory than what I was being taught, and I believe I did that. This video is targeted towards people who have some experience with linear algebra, in particular linear transformations, but I'll review the basics for anyone unfamiliar with the subject. Okay, so let's start with a brief explanation of vectors. Vectors are just arrows that have a specific length and direction. And mathematically, we just represent them using a list of numbers. It's a lot like how a point in the xy plane is just a list of x and y numbers. And in fact, you can think of the vector that has the same entries as a given point as being an arrow that points to that point in the plane. However, with a vector, we're allowed to move it around freely in space so long as we don't change its orientation. Alright, so then what is a linear transformation? Linear transformations are how we change vectors into other vectors. They're best visualized as a transformation on the whole plane, shifting all the vectors at once. They're a bit like functions that take in numbers and output a new number, but instead they take in vectors and spit out new vectors. The transformations are linear because straight lines are still straight after the transformation. Here's an example of a nonlinear transformation. Okay, so let's step away from linear algebra for a moment and take a look at a physics problem. This problem is framed in the world of space-time diagrams. Space-time diagrams are just like the xy plane, except we have a time axis instead of two space axes. Lines on a space-time diagram are called world lines. They describe an object's position over time. The slope of a world line at any point will tell us the velocity at that time. We all have a space-time diagram representing our perspectives, and all the objects we encounter will have world lines expressing how they move relative to us. On your space-time diagram, your world line is always vertical, because from your perspective, you only move through time. Everything else moves relative to you. If your world line ever leaves the vertical axis, then the space-time diagram you're looking at is not your own, because you've moved in space compared to whoever's space-time diagram this does belong to. So here's the question we'd like to answer. How do we switch from the perspective of one observer to that of another observer who has a different world line? To simplify it even further, we'll just look at changing between inertial reference frames. A person's perspective is also called a reference frame, and an inertial reference frame is just a reference frame which moves with a constant velocity, which on a space-time diagram means that we have a constant slope. Here's an example. Let's think about Bob, the bystander, and Carl, the cab driver. Bob is standing stationary on the sidewalk, and Carl, the cab driver, drives past him with a constant velocity v. So here is what Bob and Carl's world lines will look like in Bob's reference frame. Bob's world line is just a vertical line because, from Bob's perspective, he only moves through time. Carl's world line has a slope of v, because for each amount of time that passes, Carl will move v times t further away from Bob. So what we would like to figure out is how these world lines will look from Carl's perspective. Let's take a look at how we do this classically first. This is how we thought change of reference frames worked before Einstein's theory. In order to answer this question, we need to assume some things to be true. 1. Changes of reference frames are linear transformations. The reason that a change of reference frame needs to be linear is because linear transformations keep straight lines straight, which on a space-time diagram means that velocities stay constant, even though that constant might change. This is important because if we have a straight line in one inertial reference frame, an object which moves with a constant velocity, and then we have some kind of nonlinear transformation to another inertial reference frame, and that same world line is now curved, we see that at different points on this line we have different velocities, which means the velocity is changing. A changing velocity is an acceleration, and because of Newton's second law, that force equals mass times acceleration, that means we now have a force in this second inertial reference frame that we didn't see in the first inertial reference frame. It is important that the laws of physics remain the same in all inertial reference frames because there is no correct inertial reference frame, so they all have to be equally valid. If we see forces in one inertial reference frame and not in the other, then one of these inertial reference frames might be right and the other is wrong. And we can't have that. They all have to be equally valid. Assumption number 2. Reference frames and changes of reference frames are symmetric. What I mean by this is that if in Bob's reference frame, Bob observes Carl moving away from him with velocity v, then in Carl's reference frame, Carl will observe Bob moving away in the other direction with velocity v. They'll see each other moving away from one another at the same speed, regardless of whoever's reference frame we're in. Additionally, whatever transformation I use to go from Bob's reference frame to Carl's, there should be an inverse transformation, T inverse, which undoes that transformation T. It takes me back from Carl's reference frame to Bob's reference frame. Finally, assumption number 3. Time moves the same in all reference frames. This one seems like it should go without saying, but as Einstein realized, and as we'll soon see, it really doesn't. Alright, so now let's actually derive what this transformation is going to look like mathematically. So let's use our first assumption. Assumption number 1, changes of reference frames are linear transformations. All linear transformations can be represented as a matrix. So our first assumption tells us that this is going to be a matrix. And I'm just going to fill out this matrix with some dummy variables because we don't actually know what the entries of our matrix should be. Alright, now let's use assumption number 2. Reference frames and changes of reference frames are symmetric. Let's think about our world lines in Bob's reference frame again. So remember, in Bob's reference frame, his world line just looks like a vertical line through time. How would we represent that as a vector? Well, it has no component in the x direction because his position never changes. What about the time component? Well, it's just whatever time t Carl happens to be at. So what about Carl's world line? Well, remember Carl's world line is just a straight line with a slope of v. So how are we going to represent that as a vector? Well, Carl's time component will also just be whatever time we're looking at. And his position, as we looked at before, will just be v times t, the velocity times whatever time we're looking at. So let's actually try and apply this transformation to Bob's world line. Well, we know that that's going to be vector 0t. And what should Bob's world line look like after we switch to Carl's reference frame? Well, remember, we have the symmetry from assumption number 2. And that tells us that in Carl's reference frame, Bob will be moving at the same velocity but in the opposite direction. So his vector should look just like Carl's does in Bob's reference frame, except we should have a negative vt. Because for however much time has passed, Bob will be v times that time away from Carl in the opposite direction. So now that we actually have an equation, we can start to solve for some of our unknown variables inside of our matrix. So for people who don't know how to do matrix vector multiplication, for this first example, I'll walk through the steps. But after this, I'm just going to do the matrix vector multiplication, and if you ever get lost while I'm doing the algebra, just come back to this first example and I'll be doing exactly the same thing. So what we do is we take the first component of our matrix and the first component of our vector and we multiply them. So A times 0. And then we take the second component of our matrix and multiply it by the second component of our vector. And then we add those together and we set them equal to the first component of our answer vector. And that gives us one equation, and then we do the same thing but with the bottom row of our matrix. So we take the first component and multiply it by the first component of the vector, and then we add that to the second component of the second row of our matrix times the second component of our vector. And then we set that equal to the second component of our answer vector. Alright, and so now we just have two equations and we can just apply regular algebra rules and solve for some of these variables. So first, we should just note that we have something times 0 in both of our equations, so those will just go away. And now, let me take equation 1 and divide both sides by t, because t is just an arbitrary time. Here, it's also important to note that we've actually used assumption 3, that time moves the same in all reference frames, because the t on this side of the equation and the t on this side of the equation are the same variable, t. We're able to assume that because it's one of our three axioms. Again, I just divided both sides by t, and we get that b should be negative v. And I'll do the same thing for equation 2. Divide both sides by t. And there we go. We've already solved for two of our unknowns in our transformation matrix. So now let me rewrite the matrix, filling in what we found. So what other information can we use to solve for our last two variables? Well, we can look at what happens to Carl's world line as we change reference frames. So we know that Carl's world line begins in Bob's reference frame looking like the vector v, t, t. And what will Carl's world line look like in his own reference frame? Well, we already know. When you're in your own reference frame, your world line always just looks like 0t. Because in Carl's reference frame, he'll only be moving through time. Okay, so I'm going to do the matrix vector multiplication again, and we'll get some new equations. So now I'm going to take equation 1, and I'm going to add vt to both sides. And then because v and t are arbitrary velocities and times, I'm going to divide by those, and we get that a should be equal to 1. Now in equation 2, I will subtract t from both sides. And since v and t are arbitrary times, we divide by v and t, and we get that c should be equal to 0. And there we go. We found our matrix, which takes us from Bob's reference frame to Carl's reference frame. And now let's actually apply this transformation to an arbitrary position and time vector and see what happens. Well, our position result is something that will look familiar to physics students. It's what you're typically taught as the formula for changing reference frames to an inertial reference frame with a velocity of v. And we get that the time component is still just time, which is good because that was our third assumption. Now let's take a look at what this transformation actually looks like geometrically. So here is Bob's world line, and we're in Bob's reference frame right now, so of course his world line is just the vertical line. Carl's world line is just this line and it has just some slope v. Now we want to change to Carl's frame of reference, so we'll apply the transformation we just found, and it looks like that. And so we see we got all the results that we want. Carl's world line is now vertical, he's only moving through time, and Bob's world line is moving away in the opposite direction with the same slope v. It's also important to note, if we look at the horizontal lines as we apply the transformation back and forth, they stay horizontal and they stay spaced the same amount. That's because each horizontal line represents a tick mark of time, 1 second. And so they're the same in both reference frames because we assumed that time would be the same in both reference frames. This transformation is called a boost. I guess because you're getting a boost in your velocity to move from Bob's reference frame to Carl's reference frame. Alright, now let's start thinking about what Einstein was pondering. Remember how I said it was important for all the laws of physics to be consistent in all inertial reference frames? Well, the laws of electromagnetism, and more importantly, experimental evidence, tell us that the speed of light is constant in all reference frames. And it's the same constant in all reference frames. It's not a particular property that can change for different objects like classical velocities. It's something intrinsic about the nature of electromagnetic radiation itself. But hold on, we just saw that changing reference frames changes the slopes of all lines, subtracting v from all of the velocities. So let's throw in some lines that represent the speed of light in the positive and negative x directions. And yeah, when we change to Carl's reference frame, he would say that the velocities, or the slopes of these lines, are different than whatever Bob is going to say. However, that makes the laws of physics inconsistent, so we have to rethink our assumptions. We must have made a mistake somewhere. Okay, so here are our axioms. 1. Changes of reference frames are linear transformations. The whole reason we're rethinking our transformation is because the old one didn't keep the laws of physics consistent. This first assumption helps us keep Newton's laws consistent. It helps us make sure there aren't any fictitious forces. So let's not change that one. 2. Reference frames and changes of reference frames are symmetric. This is still true for most objects, although not for things traveling at the speed of light. But we know that for Bob and Carl, they'll still see each other moving away at the same speed. So that leaves this third axiom, that time moves the same in all reference frames. So let's get rid of that and let's replace it with the assumption that the speed of light is constant. Alright, so here's the new scenario. Carl, the cab driver, has gone rogue and stolen a high-speed rocket from NASA. During that time, Bob has become an astronaut, and he's currently free-floating in space. Our situation occurs as Carl zooms past Bob with a constant velocity v. It's just like before, but now we're in space, and things are moving really, really fast. Alright, so now let me write another matrix and fill it with some more dummy variables. Okay, so here's our new matrix. Again, we're using assumption 1, that changes of reference frames are linear transformations, to tell us that this should be a matrix. What other assumptions can we use to solve for some of these variables? Well, reference frames and changes of reference frames are symmetric. So that means that while in Bob's reference frame, Bob's world line still just looks like 0t, in Carl's reference frame, we know that Bob is still going to be moving away with velocity v, and so his world line should still have a slope of negative v. However, we can't assume that time is the same anymore because we got rid of our assumption. So these variables need to be different. So we'll call the one on this side t prime to denote that it's not necessarily the same as the t we started with in Bob's reference frame. So let me just do my matrix vector multiplication. And so here, equation 2 gives us a definition for t prime that we can plug into equation 1. And now, the time that we have on each side of the equation is the same variable, and since it's an arbitrary time, we can just divide out by t. And so we get that f is negative vh. And just like before, let's look at what happens to Carl's world line next. We still start out with the same world line, VTT, and when we change to Carl's reference frame, his world line should just be vertical, because he'll still just be moving through time in his own reference frame. However, it might not be the same time as in Bob's reference frame, so we'll use T prime again. Here, equation 2 gives us a definition for T prime in this specific situation, but this won't really be useful for us because we don't have anywhere to substitute T prime. So we'll just focus on equation 1. I'm going to move HVT to the other side, and we can just divide both sides by VT, and we get E equals H. And then writing our matrix with this new information. Alright, what other information can we use? Well, we still have assumption 3. The speed of light is constant in all reference frames. What this means is the world lines which describe light, or photons, will have the same slope in Bob's reference frame and in Carl's reference frame. What will that slope be? It'll be this constant c, which represents the speed of light, 2.99 times 10 to the 8 meters per second. Notice that the vector describing the world line for light looks just like the vector that describes Carl's world line, except instead of v we have c, because c is the velocity of light. And it should be a vector with the same slope in Carl's reference frame, except now we have t prime instead of t. And this should look familiar to anyone who's taken linear algebra, because these vectors are the eigenvectors of this matrix. They're the vectors that retain their slope after the transformation. They stay on the same span. Now let's do this multiplication and see if we can solve for anything. Here, once again, equation 2 gives us a definition for t prime that we can plug into equation 1. Okay, and now we can distribute this c inside of the parentheses. Notice we have the same term hct on both sides, so we can subtract that from both sides. And then we can divide both sides by t. And then to solve for g, we'll divide both sides by c squared. And so g is negative h times v over c squared. So we've got this one pesky variable h that's just sticking around. It's popping up in all of our matrix entries. So how are we going to solve for it? Well, at first glance it seems like we've run out of assumptions that we can use to solve for new variables. However, there's another part of assumption 2 that we can use. Remember, changes of reference frames are also symmetric. So when we're in Bob's reference frame, Carl appears to be moving away with velocity v to the right. And in Carl's reference frame, Bob appears to be moving to the left with that same velocity v. This transformation that we're solving for, this matrix, let's call it L, takes us from Bob's reference frame to Carl's reference frame. But we know there will be some other transformation, L inverse, which takes us from Carl's reference frame back to Bob's reference frame. L and L inverse undo each other. However, let's say we started in Carl's reference frame and we were trying to figure out L inverse. Well, what's the difference between the situation in Carl's reference frame and the situation in Bob's reference frame? Well, besides the fact that Carl is in a rocket ship or whatever, the only difference that actually matters between these two situations is the velocity of the moving observer. In this reference frame, the moving observer moves with a velocity of v to the left, and in this situation the moving observer moves with a velocity of v to the right. That's the only difference, is the sign of this v term. So that tells us that all the logic we use to solve for L is exactly the same for the situation for L inverse, except that instead of v, we have negative v. So L inverse should be a matrix that looks just like L, but all the signs of v are flipped. So here are L and L inverse, and again, notice the only difference is that there are negatives on the v's in L, and because we would plug in a negative v for L inverse, those negatives would cancel and there's no negative signs on these v's in L inverse. So how is that going to help us solve for h? Well, let's try applying L to just an arbitrary spacetime vector and see what happens. So we're just applying L, our transformation that takes us from Bob's reference frame to Carl's reference frame, to some random vector on our spacetime diagram, xt. Well, what are we going to get? Well, we're just going to get some vector, x prime t prime, in Carl's reference frame. What are x prime and t prime going to be? Well, we just apply our matrix vector multiplication to find those. And I'm just going to go ahead and factor an h out of everything, just to make x prime a little bit simpler. So what is t prime? And again, I'm just going to factor an h out of everything to simplify. Okay, so now we've found this vector x prime and t prime. Well, now we can use L inverse that we solved for to take x prime t prime back to xt. So what will happen if we apply this inverse transformation to the vector x prime t prime? Well, remember, this just takes us back from Carl's reference frame to Bob's reference frame where we started. So this is just going to give us back the vector xt we started with. And how does that help us? Well, we know what x prime and t prime are in terms of x and t. So we should be able to eliminate some variables that way. So let me actually apply this matrix to x prime and t prime. So we have h times x prime. Well, we know that x prime is this term with an h out front, and so that's just going to give us an h squared. And then we need to add to that vh times t prime. And again, t prime will have an h out front, so we're going to get vh squared in front of this term. And this should just be equal to x. And now, before we do the second part of our matrix vector multiplication, let's just simplify this a little bit, because we can pull some things out, like this h squared we can pull out in front of everything. And let's just distribute this v inside of these parentheses. Well, look at this. We've got minus vt plus vt. Those are going to cancel out. And now we have an x that we can factor out of the parentheses. And that lets us cancel the x from both sides. And that's already enough for us to solve for h. We don't even have to do the second part of the matrix vector multiplication, which is great because I'm sure you're all sick of algebra by now. So to solve for h, we'll divide both sides by that term. And then we just take the square root of both sides, and we found h. And I'm going to actually rename h to the Greek letter gamma, just because that's what we use to represent this value in physics. So now we can finally write our final matrix in terms of gamma, where again, gamma is just 1 over the square root of 1 minus v squared over c squared. So before we take a look at what this transformation actually looks like, I want to show you guys one more thing. Let's think about what happens when v is much, much smaller than c. It's a very low velocity. So what happens to gamma? Well, if v is much smaller than c, then v squared over c squared is going to be a very small fraction. In fact, we can say that v squared over c squared is approximately equal to 0. So what happens to gamma if that term is 0? Well, gamma is equal to 1 over the square root of 1 minus 0. 1 minus 0 is just 1, and square root of 1 is 1, so gamma will be approximately equal to 1. So how does that help us? Well, let's fill in 1 for gamma everywhere in our matrix. But look, this term is v, which we said is much, much smaller than c, divided by c squared, which is going to be huge in the denominator. So that also is basically 0. Look familiar? It's exactly our classical change of reference frame matrix. So for low enough velocities, that matrix is essentially correct. That is the correct transformation, which is why it seemed so right, because it's just a simplified version of this more complex transformation that we found. All right, what you've all been waiting for, if you've actually waited through this whole video to see it, let's go ahead and look at this transformation. This transformation is called a Lorentz transformation, and so the matrix that we found I like to call the Lorentz matrix. So I've added these 45-degree lines which represent the speed of light, and that means that the scale for this graph is 1 second for each tick mark on the time axis, and 1 light second, the distance that light will travel in a second, for every tick mark on the x-axis. So now we can actually visualize this sort of abstract concept of changing reference frames, and we can look at how it affects space and time. So again, we have Bob's reference frame, and his world line is a vertical line. And then we have Carl, and Carl's really booking it. He's moving at half the speed of light. See, he moves 1 light second every 2 seconds. Now let's go ahead and change to Carl's reference frame. And so we see the graphs doing this weird sort of squishing along one line with a slope of c, and stretching on the other line with a slope of c. And that allows those slopes to remain unchanged while everything else moves around. And we got everything else we asked for. The speed of light is constant. Carl appears to only be moving through time in his own reference frame. And now Bob is moving away with velocity negative v. The same velocity as Carl, but in the opposite direction. Here's something we might notice. Let's look at what happens to the horizontal lines. In Bob's reference frame, these horizontal lines represent each second that ticks by. However, when we change to Carl's reference frame, those are clearly not horizontal anymore. So what Bob thinks of as the steady tick marks of time are not at all that in Carl's reference frame. So that might get us to start thinking about how this transformation is going to create some weird effects. It's going to have some weird predictions. So let's try and think about what some of those predictions are. While we're looking at them geometrically, I'm also going to throw up on screen how you would find the related equations using the Lorentz matrix. So let's try and think about what happens to time. Let's just mark one of those steady horizontal lines in Bob's reference frame. Where this intersects Bob's world line represents when he says 1 second passes on his clock. Let's change to Carl's reference frame and watch where that intersection goes. So here's the intersection where Bob says that 1 second has passed on his clock, but if we look at where that intersects the time axis now, it's at 1.155 seconds. So Carl is going to see Bob's clock is running slow by a factor of 1.155. But here's the most interesting part. We didn't have to start in Bob's reference frame. We could have started in Carl's reference frame. And because these transformations are symmetric, if we looked at where 1 second was in Carl's reference frame and then we changed reference frame to Bob's reference frame, Bob would see Carl's clock running slow by the same factor. So they'll both say that the other's clock is running slower than they think it is. This effect is called time dilation. So what's going to happen to lengths? Let's imagine that in Bob's reference frame, he's measuring the length of a yardstick. One end of the yardstick is where Bob is, and the other end is 1 light second away. So it's a light second long yardstick. And he measures the yardstick at time 0. Let's look at what happens to its length when we change to Carl's reference frame. In Carl's reference frame, one end will still be at Bob's position, but the other end isn't at a full light second. It's at 0.866 of a light second. So Carl will say, "Hey Bob, your light second long yardstick is not a light second long." And Bob will say, "Don't talk to me, Carl." And this effect of shortening things that are moving at high speeds are shorter in length, that's called length contraction. Here's another interesting one. Let's think about what happens to light. So let's say that 2 beams of light pass by Bob at time 0, one in the positive x direction and one in the negative x direction, represented by these lines that we already had for the speed of light. Let's say that Bob measures the wavelength of both beams of light to be 1 light second long. One way he might measure this is he might note when a peak passes him, a peak of the wavelength of light, and then wait until a full wavelength has passed him, and then check where the endpoint is. In this case, a full wavelength will have passed him in 1 second, and it will be at position 1, 1 light second long, and it'll be -1 light second for the other beam of light. So where these green lines intersect these light world lines are representative of the wavelengths. How are those wavelengths going to change when we change to Carl's perspective? In Carl's reference frame, those wavelengths, those intersections, are drastically different. This intersection has moved all the way to 0.577 on the x-axis, and the light moving away from Bob has a much longer wavelength of 1.732. So light going in the same direction as Carl seems to have a shorter wavelength, and light moving away from him seems to have a longer wavelength. This is called the Doppler shift. It's exactly the same phenomenon as when you hear a siren coming towards you and it sounds higher pitched, and then when it moves away from you it sounds lower pitched. The frequency is higher when it's coming towards you and lower when it moves away from you. The same is true for light. It has a higher frequency or shorter wavelength in the same direction as Carl, or a longer wavelength and shorter frequency when it's moving away. And again, for anyone familiar with linear algebra, the factor by which these wavelengths change is actually the eigenvalue of the matrix, the two eigenvalues, because it's how the eigenvectors are scaled. Okay, and lastly, let's try and think about what happens if we try to change to a reference frame moving at the speed of light. Well, we see the whole plane sort of collapses and then disappears. This is because in the gamma term, we're actually dividing by 0. So let's take a look at that. So we were looking at the situation when v is equal to c. What if I want to switch to a reference frame moving at the speed of light? Well, if v is equal to c, then this fraction becomes 1. And so we get that gamma is equal to 1 over the square root of 1 minus 1. 1 minus 1 is 0, and this is in the denominator. We're dividing by 0, and so it doesn't even make sense to think about reference frames moving at the speed of light. Well, what about reference frames greater than the speed of light? What if v is greater than c? Well, if v is greater than c, then v squared over c squared is greater than 1. So we're going to have 1 minus something greater than 1. That's going to be a negative number. We'll call it negative n. If I have 1 over the square root of negative n, that's going to be 1 over I times the square root of n. We're going to get some imaginary number. And so, again, it doesn't make sense to think about a reference frame which has imaginary components. So it just doesn't make sense to think about reference frames that are at or larger than the speed of light. And so that's why the speed of light is this sort of cosmic speed limit. It's an upper limit of what velocity you can possibly have. And with that, that's the end of my video. Thanks for watching, if you're still around. I hope you learned something, and if you want to like and subscribe, I guess, that's something you're supposed to say. I'm just going to stop recording now. And here's a little bonus challenge for anyone who feels like they have a good grasp on using matrices and vectors to solve these kinds of problems. Imagine that there's a third person moving past Bob and Carl, Amy, and Amy has a velocity u in Bob's reference frame. See if you can use the Lorentz matrix to figure out what Amy's velocity looks like in Carl's reference frame. Okay, bye.